Hello everybody. Today I will present our work about the introduction of quantum error mitigation into a QAOA workflow. But let's start from who I am. I'm Marco Venere, a PhD student in information technology, but also a student member at the Quantum Open Source Foundation, which is the context inside which we made this project. And my main research interests regard quantum computing and also reconfigurable architectures, so FPGAs. Well, the context of this project is about solving optimization problems with quantum computers. We know that optimization problems are everywhere, in industry especially. For example, in electronic design automation, we need to do place and route by solving a number of optimization problems. While in cryptography, we exploit optimization problems to solve, to encrypt or decrypt messages and guarantee security. But most of the optimization problems are very hard to solve. We say that they are NP hard, and this means that we can only achieve very imprecise solution in an affordable amount of time. On the other side, in the last years, a new paradigm of computation has been spreading out, which is quantum computing. In the last talk by Dr. Fajin, we had a glance about what quantum physics is and its laws. Quantum computing builds upon the laws of quantum physics to accelerate computation and get, in some cases, an exponential speed up with respect to classical devices. In the last years, we had some very good milestones. For example, Peter Shor managed to break RSA crypto systems in 1994. And in the last years, companies like Google or IBM managed to solve some specific problems in an incredible amount of time with respect to classical computers. And in this work, we focus on an algorithm which enables us to solve optimization problems on quantum devices. This algorithm is called Quantum Approximate Optimization Algorithm, or in brief, QAOA. And its workflow is very neat. We start from an optimization problem that you can see on the left, which is given in a mathematical formulation. And based on that mathematical formulation, we build a quantum software described as a quantum circuit, where we have some gates describing specific operations. These operations are parametric, which means that we need to find values for those parameters. And so we use a classical optimizer, like for example Powell, Kobyla, or Nethermeads, to find the best values for those parameters. And at the end of the process, if the parameters are optimal, we get the optimal solution to the optimization problem. Even though this process is neat, we have an issue, which is noise. Current quantum hardware is terribly noisy, and a lot of errors are introduced during the computation, meaning that the final output that we get often is wrong. This is why in this work we want to mitigate the effects of noise by introducing an error mitigation technique, specifically the zero noise extrapolation, and we do that as an open source contribution for the community. Also, we wanted to benchmark the effects of error mitigation by focusing on the maximum cut problem, which is a well-known optimization problem, by considering a real noise model, which is a real quantum hardware given by IBM. The error mitigation technique that we use is the zero noise extrapolation, as I was saying before. And just to give you a brief overview about how it works. Here on the left, you can see quantum software that we want to mitigate against the effects of noise, described as a circuit. What zero noise extrapolation does is it gets a statistical model starting from this circuit, where it finds a correlation between the intensity of the noise of the quantum hardware and the effects on the output. So, given the noise, I understand what the output is. At this point, what I can do is I can do some measurements in my noisy device and extrapolate what the correct output should be if noise were zero. And this is how it works, basically. So we integrated zero noise extrapolation in the process, and then we wanted to benchmark its effects with the maximum cut problem, considering as main key performance indicator the approximation ratio, which is a metric used in the state of the art to understand the accuracy of our QAOA workflow. And we focused on the IBM Brisbane as quantum hardware, which provides a noise model to verify. So here you can see a bunch of experiments that we run to understand the accuracy of the model. In the green box on the left side, you can see what happens in a noiseless environment. So QAOA performed correctly. The approximation ratio is maximum because we don't have any kind of noise. Now let's introduce noise without any kind of mitigation. As you can see, approximation ratio reduces considerably because of the effects of noise and errors in the computation. Then we test different configurations of Z and E, so error mitigation, and we see that all of them achieve a better accuracy in the middle between the noisy case and the noiseless one, which is what we expected. So great, it works. And also what we can notice is that even though we change the configuration of the DNE, so we change the hyperparameters of the error mitigation, we don't get a best winning configuration, which means that it is really dependent on the instance of the problem. So there is no best performing configuration. As possible takeaways from this study, we can say that ZNE effectively works, and we managed to solve optimization problems on quantum device by reducing the impact of errors. But on the other side, we're talking about a framework consisting of a quantum computer, but also a classical optimizer. So the same problems that classical optimizers have in the classical world also reflect on the quantum world, such as the presence of local minima, which may be a problem, an issue for the classical optimizer because it may get stuck in such minima. As a next step for this kind of work, we want to integrate further error mitigation techniques and verify if they behave in the same way as zero noise extrapolation. With this, I thank you all for your attention, and if you have any questions, we can meet and discuss together. Thanks.